Right. Let's say we rotate all bones by the same amount around the same axis. What should happen to the mesh? Why would it remain the same? If I am transforming each and every bone, why will it remain the same?
There will be relatively no change with respect to each.
Agreed. So the shape will remain the same. That's what you're trying to say. Right. That's fine. But will there be no change at all?
No, means it will
Exactly. You expect that the entire mesh will also rotate by the same amount. Now, unless you have this condition, will that happen? Yeah. Unless you have this, will that happen? See, what you are going to do is, in order to compute the transformation at a vertex, you are going to do a weighted combination of all transformations on the handles. Right. So, maybe I should have written that equation first. So, the transformation on vertex I can be written in this way: all handles Wij Tj, where Tj are the handle transformations. Right. So, if all Tj's are the same, right, unless summation of Wij is 1, Tvi will not be equal to Tj. Okay, so for that particular reason, we impose this partition of unity condition. The other condition is we want the weights to be non-negative. Why? What happens if the weight of one handle at one vertex is, let's say, negative?
vertex from one direction, the bone will move in the other direction.
Exactly, right? It will have the opposite effect. So, let's say I am translating a bone in this direction, but its influence at some vertex is negative, right? And if you do something like this, you will get the opposite transformation on that vertex, which is sort of non-intuitive. Okay, so we expect that the weights should be non-negative. How are you going to solve this problem? This one? So, the value of the weight J at handle K is given by, so this is the Kronecker delta. Only if K is equal to J. Everywhere else it will be 0. Okay, so yeah, maybe I should have explained. This is the Kronecker delta notation. I don't know if you are aware of that. So, delta Jk is equal to 1 if K is equal to J. For all other values of K, it is 0. It is just encoding the same constraint that the influence of handle J on itself should be 1, on all other handles it should be 0. Right. So, how do we solve this? How do we solve this? What sort of a problem is this? Constrained optimization problem and non-linear, of course. So, how do we discretize this? Because this delta, right, is on a continuous surface. Okay, but on a computer, of course, you will be working with meshes. So, what is the counterpart of delta on mesh? That is what you have studied, right? Discrete Laplace Beltrami operator, which is M inverse L. I don't know what is the notation you are familiar with. This is the cotan weights. This is the mass matrix. Did you go through this? No? Okay, then I will not get into the details of this anymore. But so, yeah, basically it turns into something like this. So, you have these matrices. This is a diagonal matrix typically, and then this will just be L, M inverse L. Half. Okay, so this will just be a matrix. So, you have a quadratic optimization problems. All the constraints that you can see are linear, okay, on the weights. So, it is a quadratic optimization problem with linear constraints. Equality, the first two, the third one is an inequality condition. Okay, there are solvers available in Python, MATLAB, whatever you want, right? And all you have to do is to feed in this matrix, write these as a matrix. This also, there are, I think, lower bound and upper bound conditions that you can provide directly. It will spit out your bounded by harmonic weights. Okay, so it will look like this. Okay, so compared to the inverse weight functions, you can see that there is no influence of this handle over here. Okay, even though in the Euclidean space they are close by. It's simply because we are using an intrinsic property of the surface to define these weights. This one. So, functions that satisfy this equation are called harmonic functions. Okay, you have Laplacian squared over there, so that's why biharmonic. Okay. There are also one or two other conditions that these weights satisfy, which is sort of important. I have not written it on the slides. One condition is that these weight functions should not have a local minima or maxima. So, in the sense, if you take, let us say, this example here, right. So, if this is the handle, the weight should not sort of decrease, then increase, and then again decrease, right, because it is like you are moving away from the handle. So, the influence is reducing, but then suddenly again it is increasing, and then suddenly again it is decreasing. That should not happen. Okay, otherwise sort of the portion where suddenly the influence starts to increasing will sort of follow that handle, everything else will follow other handles. Okay, so there is another property of these bounded biharmonic weights, that it guarantees theoretically that these weights will not have local minimas or local maximas.
So, we were concerned about, like, if we move the hand, the thigh will move. How does this solve that problem?
So, unfortunately, because there were like 1,75,000 vertices, I could not get around to computing it, but you can see over here, right. If I were to plot the inverse distance weights here, there would be a portion of this, right, the top of the main stem of the cactus, which would also be under the influence of this handle, because in the Euclidean space they are close by. So, the same thing for the human mesh, right.
Yeah, they solved it, but how? How did it solve it?
Because this Laplacian, right, I said this Laplacian is what Laplacian. Okay, so it is an intrinsic property of the surface. So, we will have the Euclidean distance is not considered at all. Okay. Then, so that is sort of the first part of skinning, the weights. Next part is transformations, right. So, we said that the user is going to specify transformations on the handles. Okay, so Tj are your handle transformations. Now, typically it is always the case that all these handles, right, they will undergo a rigid transformation only. For example, if you think of the bone structure, right, in a human mesh, you will not suddenly bend the bone, right? You will not expect the user to bend the bone. Okay, so we'll assume that the user always specifies a rigid transformation on the handles. I'm not saying that all the mesh will undergo rigid transformation, no. Okay, even the first example, if you recollect the humanoid mesh uh, change in the hand pose, that's not a rigid transformation of the entire mesh. Okay, but in that example also you could sort of think that the points on the end points on the fingers, right, they underwent a translation. So translation is a rigid transformation. Okay, or you can expect that the hand is sort of rotated via the bone. So that also is a rigid transformation. Okay, rigid transformations can be characterized by transformations which preserve the Euclidean distance. Okay, and then you can derive that rigid transformations consists of only rotations, translations, and if you sort of accept change in orientation, then you can also include reflections. Okay, but there are only these three transformations in the class of rigid transformation. So rotation, reflection, translation. You can't do anything else. Okay, we will also not allow reflections because that will be unnatural for the user. You can't expect the bone to reflect about its own axis, etc., etc. So therefore, we will limit our attention to only rotations and translations. Okay, and you may be not sure if you are aware of this notation, but the set of rotations and translations, they form a group, okay, which is called the special Euclidean group of order 3. That is not very important. The set of rotations alone, right, they also form a separate group in themselves. Which one? This one? SO. So the set of rotations form a group which is called special orthogonal group of order 3. What is the characteristic of a rotation matrix? Orthogonal and determinant is 1. Okay. So just orthogonal will also include reflections. If we additionally say that the determinant has to be +1, then you will end up with only rotations. Okay, now if you want to apply these transformations to vertices, right, remember translation is not a linear transformation. Okay, so therefore you directly cannot include it and write it as a matrix, so you will have to use what are known as homogeneous coordinates. Okay, so you will artificially include a fourth dimension and therefore you will have a 4 by 4 matrix. The top 3 by 3 top left portion of it will include the rotation matrix. The last column will include the translation. The last row would be all zeros and last entry would be 1. In order to apply this to a vertex, all you have to do, if your vertex coordinates is given denoted by this vector v, you will add a 1 below that to obtain a 4 by 1 vector, and then you can directly multiply this 4 cross 4 matrix to this 4 cross 1 matrix to obtain your deformed vertex. The first 3 entries will be the coordinates of your deformed vertex. Okay. Yes. Once again,
What is that matrix components are?
R is your rotation matrix.
ARER. What are the elements are?
Which R? This R? No.
ARER. I'm saying R, the word R.
Okay.
I'm saying what are the components are? What is R3 cross 3T? 3 cross
So
2?
R3 cross 3, this one, that's a rotation matrix.
Rotation matrix. And T?
T is your translation vector.
Oh, translation.
Okay. Maybe so they will experiment with them in the afternoon. Let's see what happens.
Briefly under graphics design.
Oh, you've done graphics, then yes, you surely have played around with rotation matrices. Okay. So what part is not clear? Please ask. I mean,
Defining like Tj, that means each of these element you are defining, right?
no. Rj, Tj is the rotation and translation that is applied at handle J.
Okay, that means this T tilde matrix is the whole matrix. Right?
Yes. So this is encoding one handle transformation.
Okay, but I'm not getting.
J. Forget the J.
Why are you writing J there?
J is in order to ensure continuity with this. Where is it? Thought I had written Tj somewhere. Yeah, this Tj. So if I want to write the jth handle transformation as a 4x4 matrix, forget the J and you will have this. Yeah. So if you want, you can put a subscript J here as well. T tilde J is Rj 3 cross 3, Tj 3 cross 1.
So, domain of T is what? Like,
Domain of
T is from where to where?
which T?
Like Tj, sorry, Tj is from where to where?
So it will be applied on a vertex.
Okay, so RJTJ is in SE of 3. That is
So
okay.
the transformation will be of the form, there will be a rotation matrix, the rotation component and a translation component. So the rotation component will be denoted by this 3 cross 3 matrix R, and the translation component, which is basically one vector, that's T. So this tuple R and J are elements of the set of Euclidean transformations.
So, is there any reason to put the next row 0 and 1?
Yes, so the reason is since translation is not a linear transformation, but if I want to apply it as a matrix, yeah. Right. Any questions? Okay, I mean, if this 4x4 thing is confusing you, forget that. It's not really going to play a major role. It's just one way to apply translation also as a matrix, right, which traditionally you cannot. But yeah, basically again the take away message is each handle transformation will be a combination of a rotation and a translation. Okay, and at different handles, of course, you can have different rotations and different translations. Okay, right, let's talk about rotations then. Right, as we agreed, rotation matrices are orthogonal matrices, okay, whose determinant is +1. Okay. How do I represent rotations, right? There are different ways in which I can represent rotations, 3D rotations. One is Euler angles. Have you heard of this? No, okay. So any 3D rotation can be specified as a combination of rotation along the x-axis followed by rotation along the y-axis finally rotation along the z axis. Any 3D rotation that you want to construct is a combination of these three basic atomic rotations. Okay, you can write them in this way. So these are, I think this is Rx, rotation along the x axis, y axis and z axis. Product of these three matrices will also be always a rotation matrix.
So we can say like this is rotation about x-axis. Second
Which one?
First one is rotation about x-axis. Second one.
This is rotation about x.
The first one,
Yeah, individually.
first one to be about x, second to be about
Y, this is about z.
No, first one I think about.
This is about z.
Yeah. Oh, sorry. First one, that side is about x-axis.
Yeah, this is about x axis, this is about y, this is about z. Sorry? Oh yeah, I messed it up, sorry. Yes. Yeah. So this should be in principle theta x. It should be theta y, this should be theta z. Yes. That's what happens when you copy paste with them. Right, yes. Thank you for spotting that error. So this should be theta x, this should be theta y as it is, this should be theta z. Sorry, theta, yeah, theta z, yes. Okay. So the idea is rather than using 9 numbers, right, because you have finally a 3 by 3 matrix, so you will have to have 9 numbers, right. Rather than using 9 numbers, you can represent any rotation with only 3 numbers, right, rotation about the x, y and z axis. That's the advantage of this. There any issues with this particular representation? Yes.
it's still a matrix, so I have to do computations.
While applying, yes, but if you just want to store these rotation matrices,
I don't remember exactly, but there is some issues with the rigid body transformations when you use Sawyer angles. Apparently, they don't rotate properly. That's why we use alternate.
the reason is a little incorrect. But yes, I mean there are issues, agreed. That's what I'm asking. So any issues with this? So is this a unique representation? And can I change the order of this? Will it remain the same angles? So if I first use z, then y, then x, or first x, then z, then y, will it be any different? Sorry?
It will remain the same, means same transform overall.
It will not remain the same because these matrices are not commutative. Okay, so there is basically no unique order in which you can apply these atomic rotations. In fact, there is no need even to apply all these three different atomic rotations. You can get all rotations by, let's say, Rx, Ry and again Rx. You don't even need Rz. Okay, so one issue is there is no uniqueness here. The other issue is what happens if I substitute theta y here equal to pi by 2? Can you multiply the all the three matrices out and see what you obtain? 0. What? Which one will be 0? Why would this be a 0 matrix? Figure it out. I mean, I don't think this is difficult, right? Just substitute theta equal to pi by 2. I'm not asking what happens to this matrix alone. right? After obtaining this matrix, multiply these three matrices out and see what you get.
Only theta y or everything?
No, only theta y equals pi by 2. And I think once you give me that answer, I guess we can break 40. It's 11, so. My question is, what is the product of these three? Rz, theta z, Ry, pi by 2, Rx, theta x. It has to be a matrix, right? What do you mean by one? It's up to you. It will have no impact on the end result. So you can either continue with my typo, including my typo, or you can correct it and do it, whatever. Maybe a set of you could figure out the first column, the other second, and the third column. Done? Okay. First column,
0, 1, okay. 0, 0, 0.
all three zeros.
No, that is 1.
Yeah, there's some error then. It will be a rotation matrix. Rotation matrix cannot have a column of all zeros. So 0, 0, 1. Okay.
Minus sign
Minus sign.
of theta x theta z.
No, minus
Sign of theta x plus theta z.
theta x plus theta z.
I'm not done with this. I'm not done with this.
Okay. This
Then this.
second column,
Cos theta z
cos theta z.
into cos theta x. There's an identity going on which I haven't figured out, but yeah, I think it ends up being a rotation matrix of the diagonal being theta x plus theta z.
Right. Something like that. This will be cos Something like this should be there eventually. Am I right? One, yeah, I think so. Can somebody confirm that? Then we can move on. Like this.
But I forget what the identity is like. Which one is cause?
Oh, that's fine. Okay, let's assume this is right. What is the conclusion about this? Do you see any issues here? Sorry? Did you say something? No. Okay. Do you see any issues here? Sorry? -1, no. It's +1. So surely this has to be a rotation matrix, right? Its determinant has to be +1. What is the issue here? So all you have done is you have set one angle out of the three. You should remain with two more variables. Sorry?
Multiplying, it will not be again a rotation.
Multiplying what?
Like you are asking about an issue, right?
Huh.
After doing this, I think it's not again a rotation.
Okay. So this is a rotation matrix. Then what is the issue? Product of two rotation matrix is guaranteed to be a rotation matrix, right?
There in main diagonal one will come.
No. Where? Okay, so do you spot the issue here? Are you left with two variables? Which two variables? Really, are you left with them? See, this rotation matrix depends not on theta x and theta z, but depends on their sum. So if I say theta x is something, theta z is something, and then I increase theta x and theta z, right, or increase one and reduce the other, we'll still end up with the same rotation. So you really don't have two variables with you, it's only one variable. Right? So you just set one rotation, right? So this is what is called gimbal lock. Okay, this is the loss of 1 degree of freedom. And I believe this has actually happened on spacecrafts and with certain issues. This has led to certain actual issues in navigation. Okay, so I think we'll stop here for now and then we'll continue with other representations of rotations. Okay. Okay, so rotation matrices and rotations in 3D, we have seen two representations as of now, right? One is a 3x3 orthogonal matrix with positive determinant. The other is the Euler angle representation, right? Let's look at one more. It's called the axis angle rotation representation. Okay, so what we do over here is any 3D rotation matrix can be seen as a rotation about one single axis. Okay, of course, in this case, the axis is not necessarily the x, y, or z axis. Okay, but there will be one axis in the three-dimensional coordinate system about which this will be a rotation by some angle. Okay, so just believe me in case you're not sure of this. So if you're not sure of this, try to show that there will be one eigenvector of this matrix with an eigenvalue plus 1. Okay, from here. So rotation matrices have to satisfy this. Given that they satisfy this, try to show that any such matrix will have an eigenvector with eigenvalue plus 1. What are you doing? Okay, right, and what does that mean? So what is an eigenvector with eigenvalue 1? That means this eigenvector has to be an axis, right? No?
Yes, because you're rotating the axis about the duality axis.
So just imagine the x-axis over here. Yeah. What does this do to the unit vector along the x-axis, or any vector along the x-axis for that matter? Does that get changed at all? Don't get changed. That's why it's called the axis of rotation. Okay, so once you show, starting with these properties, these two properties, right, you can show that there will be an eigenvector of this rotation matrix with eigenvalue 1. Once you show that, it automatically concludes or implies that that eigenvector has to be the axis about which you are rotating. Okay? Right. Yes?
Sometimes it can be minus 1, right? But you are not considering that. Determinant can be minus.
No, no, no. Determinant can never be minus 1 for a rotation matrix.
Rotation matrix is an orthogonal matrix, right?
No, I mean that's a part description.
Like it is a type of orthogonal matrix.
Yes. It's a subset of orthogonal matrix. Right. So, yeah. Right. So, that eigenvector with eigenvalue 1 will be its axis, and there will be some rotation angle about that axis. Okay. So, I can uniquely sort of represent any rotation matrix in 3D by its axis and angle. Okay. I am skipping the proof. The proof is this, right? Try to show this yourselves. Similarly, if I give you an axis of rotation and the angle of rotation that you want to carry out, can you give me the rotation matrix? So that is what is known as the Rodrigues formula. Okay, so yeah, I should maybe mention what are these strange looking notations. So eta is your axis, eta 1, eta 2, eta 3, these are its 3 coordinates. This is the matrix that sort of looks like this. And what it is trying to do is, it's trying to capture the cross product transformation. So eta cross v, we know cross products in 3 dimensions. If you want to implement this as a matrix multiplication, that will be the same as this matrix times the vector v. Okay, it's not very difficult to verify this. Right? Once you know what is the cross product of the two vectors, you can try and fill in this matrix, you will get this. It's a skew symmetric matrix. Okay, yeah, so that is what this matrix denotes. Okay, so if eta and theta are your axis angle representation, the 3 by 3 rotation matrix is given by this equation. Again, I am not going to derive this. And similarly, if I give you a 3 by 3 rotation matrix, can you give me the axis and angle? Right? How do I compute that? So that is one way. The question is, so what this equation gives you is, if I give you the axis and angle, this equation tells me what is the 3 by 3 rotation matrix. Given the rotation matrix, how can I compute the axis and angle? So this skew symmetric matrix is nothing but half times R transpose minus R. Okay, once you have this skew symmetric matrix, you can extract the axis from this matrix. The angle is nothing but cos inverse of this. This is very easy to show. Just take the trace on both sides of this equation. Okay, so if I take the trace of R, what is on the right hand side? What is trace of identity? 3. Trace of sine theta into this skew symmetric matrix? 0. Trace of 1 minus cos theta into square of this skew symmetric matrix? It's not 0. So if you square this skew symmetric matrix, you will end up with a symmetric matrix. Okay. So trace of R is 3 plus 0 plus 1 minus cos theta into, I think it's minus 2 times eta norm squared. As far as your axis is a unit vector, right, this goes to 1 and that will give you 3 minus 2 is 1, and what are we left with? Plus 2 cos theta. That's your trace of R. Right. So given a rotation matrix, you don't really have to compute its eigenvectors in order to compute its axis. Okay, which by the way is not incorrect, but it's just going to be computationally more expensive.
That is can do like how to compute that.
Which one?
Skew symmetric matrix 1 by 2 R transpose minus.
Yeah. So R transpose minus R, what is it? If you take the transpose of R transpose minus R, what will you get?
It's again a symmetric matrix.
No.
R transpose minus R. Only diagonals.
No. It will be R minus R transpose, right? It will be skew symmetry. It has to be, otherwise something wrong. Right? If I take the transpose of this right hand side, R transpose minus R, what happens? R minus R transpose, which is minus of this thing. So that's exactly what a skew symmetric matrix has to be, right? Okay, so yeah, so this is how you can go back and forth from one representation to the other. The problem is, how can you do a weighted combination of rotation matrices in axis angle representation? Weighted combinations, right? That is what you want to do in order to implement skinning. You can't just take weighted combination or linear combination of unit vectors or the axis, right? That axis may not have any relation to the original axis of the given handle rotation matrices. Okay, so that is sort of the disadvantage, especially for this application. Okay, although the representation is very nice in the sense that you have to deal with only 3 numbers, right, the axis angle, similar to your Euler angles. So you only need 3 numbers here as well, okay, but unfortunately it is not amenable for blending. So, let us look at another representation, which is quaternions. Are you all with me?